Next we have y is equal to 5 halves x, 5 halves raised to the x power minus 3. So first thing we need to do is look at our base. And even though it's a fraction, you have to be careful. 5 halves, this improper fraction, is bigger than 1. So that tells us that the basic exponential function it's based on is an increasing graph. Okay, well, we see that there's some transformations that have been done to 5 halves to the x power. So therefore, I'm going to draw that graph as a dotted red line, and then we'll apply our transformations to see what the final graph, the graph we're looking for, actually looks like. Actually, I'm going to draw it as a dotted black line. Okay, so that would be y equals 5 halves to the x power. Okay, well, what does that minus 3 on the end do to our graph? It's actually going to move it down 3 units. So what will that affect? Okay, well, if we started off with a y-intercept at the point 0, 1, and now we're moving everything down 3 units, 1 minus 3 is going to take us down to a minus 2. So that will be our new y-intercept. Also, we started off with a horizontal asymptote at y equals 0. Well, if we move y equals 0 down 3 units, that's going to take us down to y is equal to negative 3. Okay, and that's enough for us to get a sketch of our graph. So it's still increasing. All we did was move it down 3 units, and that would be a rough sketch of this graph. Let's go on to the next page. We now want to look at some applications of exponential functions, and a common one is using compound interest. An investment that earns compound interest will get interest on the interest earned. So this is a formula that you need to make sure you're familiar with. A is equal to P times a quantity, 1 plus R divided by N, all of that raised to the N times T power. Well, N represents the number of times the account is compounded in a year. Okay, so this is the number of times the account is compounded in 1 year. R is equal to the annual interest rate in decimal form. So the annual interest rate in decimal form. T is the number of years of the investment. The number of years of the investment. P represents the principal. And the principal is the amount initially invested. So that's the initial investment. And lastly, A represents the amount in the account after T years. So the amount in the account after T years. Okay, so now that we know what all of our variables represent, let's go through some examples of applying this formula. How much would an investment of $1,000 grow to in 5 years if it is invested in an account that is compounded quarterly at a 4% rate? Okay, well, we need to determine what all of our variables are. So how much would an investment of $1,000, so $1,000 is the principal, so that's P. How much will it grow to in 5 years? So my T is 5. If it is invested in an account that's compounded quarterly. Well, if something's compounded quarterly, that means it's compounded 4 times in a year. So that means N is equal to 4 at a 4% rate. Okay, well, our value of R has to be the rate in decimal form, so that'll be 0.04. So now we have all of the values we need to figure out A, the amount of the investment after these 5 years. So we see from our formula, it's equal to the principal, which is 1,000, times the quantity, 1 plus R, which is 0.04, divided by N, which is 4. All of that raised to the N times T power. So N is 4 times T, which is 5. Okay, well, let's simplify this a little bit to make it easier to put in the calculator. So we have 1,000 times, well, 0.04 divided by 4 is 0.01. So inside the parentheses we have 1.01 raised to the 20th power, 4 times 5. Okay, so the way that I'm putting this in my calculator is I'm doing 1.01 and I'm raising that to the 20th power by using the caret key. So the way that I'm doing it in the calculator is 1.01 raised to the 20th power, so that's our caret key, and then we'll do times 1,000. Because remember, the calculator will follow order of operations, so it will do the exponent before the multiplication. Okay, and it looks like we should get, and we're going to round to the nearest penny, $1,220.19. Okay, so that's how much they would end up with in 5 years. Okay, let's go on to the next example. What is the value of an investment of $500? Okay, so they're investing $500, so that's my principal. That is invested in an account compounded monthly. Well, if something's compounded monthly, that means it's compounded how many times in a year? 12. So that's our value of N. At a 1.5% interest rate, so what is R? Make sure you don't say that R equals 1.5. It has to be the decimal form. So 0.015 for 2 years. Okay, so T is our time in years, so T is 2. So to find A, we plug in all of our values. We'll have 500 times the quantity, 1 plus R, which is 0.015, divided by N, which is 12, raised to the N times T, so 12 times 2. So again, I'm going to simplify this before putting it in the calculator. Okay, so if I do 0.015 divided by 12, that's going to give me 0.00125. So when I add the 1 to it, we get 1.00125. And then we'll raise that to the 24th power, 12 times 2. Okay, So I'm going to raise that quantity to the 24th and multiply times 500, and this is giving me approximately $515.22. So when going through these problems, look back and just think, is that reasonable? If I started with $500 in an account, after 2 years I end up with $515 at a 1.5% interest rate, that sounds reasonable. If we came up with a number like 10,000 or 50,000, that would give us reason to pause and make sure we didn't make an arithmetic error someplace. Okay, going on to part C. How much would you have to invest? Okay, so if we're looking for the amount that we have to invest, they don't tell us. That means that we need to figure out what P is in this case. To have a return of $2,000, so that's going to be A, the amount in the account, after 1 year, that's T. If the account is compounded semi-annually, so what is N equal to if it's compounded semi-annually? That's going to be twice, so N is 2, at a 3% annual interest rate. So that means R is equal to 0.03. Okay, so this one's a little bit different because we know what our value of A is. So that's 2,000 is equal to our principal. We don't know it, so we keep that variable, times 1 plus R, 0.03, divided by N, which is 2, raised to the N times T, so we have 2 times 1. Okay, so let's simplify this. So the left side, we still have 2,000 is equal to P times, if we do 0.03 divided by 2, that gives us 0.015 plus 1, so we have 1.015, and this is raised to the second power, 2 times 1. Okay, well, when you're dealing with this type of problem, or really any problem, you don't want to round your answer in any intermediate steps. You only want to round once at the end. So what do we need to do here to get P by itself? Well, we need to divide by everything in parentheses raised to a power. So that 1.015 squared, we're going to divide both sides by. Right, so that'll make it cancel out on the right, and we're going to be left with P, which is what we want. So P is approximately equal to, all right, well, order of operations, the calculator follows it, so it will do exponents before it does division. So we can enter in 2,000 divided by 1.015, and you can hit the x squared key, or you can do the caret and then the 2. And it looks like we're going to get $1,941.32. So again, look at that to see if it seems reasonable. We're saying that's the amount we have to invest to end up with $2,000 after 1 year. That seems reasonable. Okay. Next example. Suppose the population of a certain species after T years is given by this function. What will the population be 3 years from now? Okay, well, 3 years from now means that 3 is playing the role of our T. The population is P. So we're looking to find what P of 3 is equal to. So all we need to do is substitute in 3 everywhere we see a T. So 790 divided by 1 plus 6e to the negative 0.1 times 3. Now let me make mention about E. This is something that you may see on the assessment, and I will let you know if that's the case. E is a number like pi. So just like you know that pi is approximately 3.14, E is a number that comes up a lot when you're dealing with investments and growth, functions that represent growth or decay. And it's approximately 2.72. And you will see that E is usually on your calculator, just like pi, so that you can get an exact value. Okay, so just keep in mind, anytime you see E, it's a number, not a variable. So now we're ready to evaluate this expression. So let's simplify the exponent first. So we'll have 790 divided by 1 plus 6, then E raised to the negative 0.3 power. All right, so the way that I'm entering it in my calculator, I'm doing 790 divided by, well, I want everything on the bottom to be computed before the division happens. So I'm going to put in parentheses 1 plus 6. Then I'm going to do E raised to the negative 0.3 power, closing parentheses. And I'm coming up with approximately 145.09. So what is the population? Approximately 145. Whatever species we're talking about, 145 of them. Let's go into our last page. Okay, we want to look at solving exponential equations with the same base. So fortunately, this I think you're going to find to be very straightforward. So let's say that we have b raised to the x power is equal to b raised to the y power. Well, what do you think we can conclude? Since the bases are the same, the only way that that can happen is if the exponents are the same. So we can conclude that x is equal to y, and then we just need to solve that resulting equation. So let's solve these equations in our example. So we have 3 raised to the x plus 1 equals 3 raised to the 2x minus 3. Since the bases are the same, that means the exponents must be equal. And now we have a simple linear equation that we know how to solve. So I'm going to subtract x from both sides to get my x's over to the right. And I'm going to add 3 to both sides to get my numbers on the left. So it looks like we have 4 is equal to x. And that's it, because we have our variable x by itself. So if you plug 4 in for the x's, you'll see that this checks out. Moving on to part B. For this equation, notice that the bases are not the same. Therefore, we cannot yet apply that rule. However, I know that I can rewrite 4 as a power of 2. So we're going to leave 2 to the 5x the same. And now we can rewrite 4, because 4 is the same as 2 squared. And we still have the that's raised to the x plus 1 power. Okay, so we're closer to a solution. Still leaving 2 to the 5x. If you have something to a power raised to another power, one of our rules of exponents says you're going to multiply those two exponents together. So we have 2 raised to the 5x power is equal to 2 raised to the, now make sure that you distribute the 2 inside your parentheses. So we'll have 2 raised to the 2x plus 2 power. Now our equation is in the form where we can apply that rule, and we get that 5x is equal to 2x plus 2. Subtract 2x from both sides, and we have 3x is equal to 2. Divide both sides by 3, and we get that x is equal to 2/3, and that's our answer.